So the question is, can we solve this given differential equation? And the first thing is, ask yourself, is it a separable differential equation? Can you take this and factor it in terms of a function, in terms of x, and in terms of y? I'm not seeing it. The next thing is it one of those first order ones we talked about so that you can hit it with the integrating factor? To do that, you have to have y prime, a function in terms of x, y, and a function in terms of x, which we'll call q here. I don't really have that structure, mainly because I'm seeing like a y, and I'm seeing this y squared, and if I was to divide everything by y, it's no longer in the numerator, but now it's in the denominator. So, okay, I can't do this either. Okay, so another thing that we could potentially do is take the y prime, recalibrate it, and say dy dx. Then you could multiply both sides, shuffle some terms around. You would get 5x squared, oops, don't forget 3. 3 y squared dx minus xy dy. So just a recalibration of the given differential equation. And I see that I can call this function maybe m, and maybe call this one n. So the question is, well, I can't separate it. I can't use the integrating factor, or is it an exact differential equation? Let's take the partial of m, and because that's a dx, you take the partial in terms of y. So you have 6y, and then likewise, take the partial of, now, x, not y. You're going to get minus y. Is it an exact differential equation? No. In order to be exact, these two things would have to be the same. So the question then becomes, it's not exact, but can I do something to it so that it does become an exact differential equation so I can actually solve it? If I looked at the structure in a little bit more detail, and what I want is I want to get a nice function that's going to make this work the way I want this to work. Very similar of how we found a nice function so we can solve those first order differential equations by using that integrating factor. So what would happen then if I multiplied everything by, and instead of saying u, let's say mu. And what I want is I want mu to be the just right function so that when we do take the partial in terms of y, we will get the partial over here in terms of x. That's the goal, because then I have an exact differential equation, which then we can go ahead and solve. Well, if mu and m, if they're both functions and I'm taking this partial, I'm going to have to take this partial, I'm going to apply the product rule. Again, I'm holding the x constant. So I'll have the partial of mu with respect to y, m, and mu, then the partial of m with respect to y, partial of mu with respect to x, n, and then mu, the partial of n with respect to x. So apply the product rule. And I'm just going to shuffle some terms around because our objective is we want to figure out what mu is. It's right there and it's right there. So take this, throw it to the other side, and move things around. We have our mu of x. And that's like saying the partial or derivative. When we solve, we're going to get this function. My goodness, that looks familiar, doesn't it? Here I have this derivative, here I have the function, and then I have the function again. And if I want to solve this, that's like doing the whole entire integrating factor all over again. We take this, we would integrate, and then we would exponentiate. And if I hit it with that function, I can convert a non-exact differential equation into an exact differential equation, which then I can go ahead and solve. So what do we do when it's not exact? We can use this factor. So first compute this. Second, take this, multiply through. And this is the just right factor to convert from non-exact into an exact. It makes a lot more sense writing through a problem here. Okay, so let's go back to this one. Okay, so again, we took this and we recalibrated it. Okay, we identified the M. We got the N. Calculate the partials. Okay, calculate the difference. Divide by N. And N is going to be minus xy. Y's divide out. Minus 7 over x. So after you have this, integrate. If you integrate this function, you're going to get minus 7, the natural log of x. Exponentiate it, and you found that magical function, that mu function. But again, you want to simplify this down. Put the negative 7 back on top, use properties of logarithms and exponents. And it comes crashing down to x minus 7. Now, multiply 3 by mu. Clean it up a little bit. Distribute. Let's test it out. Let's see if it actually does work. If you take the partial of this function with respect to y, this goes away. We're going to not worry about the x, but you're going to get 6y x to the minus 7. Take the partial over here now with respect to x. What do you get? Well, take this minus 6, pull it out front, take one off the top, you get the same thing. So we have now an exact differential equation. We can grind through that process that we discussed last time. And again, it doesn't really matter if you start with this function or this function. Make your choice and just go with it. My choice is I'm just going to take this function, I'm going to integrate in terms of x, and I will get the function fxy. Treat y as constant. Now, it's not plus c, but it's function gy. We can simplify down a little bit more. So if I can figure out the g function, we're done. So the next step in the process, take the partial. So n is the partial of f with respect to y. This is given in the problem. No calculations are needed. Just look at the n function and drop it in. And you're not coming up to here. Because remember, this was not the exact differential equation. You're coming down to here and using this right here. That's going to be minus x to minus 6y. And take the partial with respect to y. What happens with this component? X is constant. What's the root for a constant? 0. Do for the next piece right here, and you're taking the partial again in terms of y. Okay, now this is the moment of truth. If we did something wrong, we're going to see it really quickly emerging right here. But I do see that this is the exact same thing that we have on the other side. The function g should not have a single x in it because it's not a function of x and y, it's only a function in terms of y. So all the x's should go away. You get 0. So let me ask you this question. I know if I integrate g, probably sure that is, I will get g back. So what is the integral of 0? It's not 0. What function, when you take the derivative, will give you 0? constant. There's your C. So come back over here and update. And you just found the function fxy. Now let's just clean this up a little bit more and get this into a nice form. Okay, so we're going to have minus 5 over 4 x to the minus 4th plus minus a half y squared x to the minus 6. And because when we take the partials, these derivatives, we're going to get 0. That really says this function really is a constant function. So that c, I'm just going to throw it to the other side. Okay, let's solve it implicitly now in terms of y. So we can multiply everything by 4, clean it up. I'm going to say 4c. And I'll just go ahead and clear this up as well. Let's multiply everything by x to the 6. And what I don't want to do is I don't want to say minus 2 times c is c, because I might have applied initial condition back here and figure out the c, or I may wait to the very end if one's given, and it might get confused. So once you got your arbitrary particular constant associated with this differential equation, leave it alone, call it c, and if you run into something like 4c, just call it something else, like call it a or call it b. Okay. Wow, look at that thing. So you can turn a non-exact differential equation into an exact differential equation by hitting it with this very interesting matchable factor. Okay, so the first thing is it an exact differential equation? Okay, I'm not seeing that. But I know how to turn a non-exact into an exact by figuring out what's happening right here. So identify the m and the n. And we're going to keep calling whatever's in front of dx, we'll call that m. And whatever's back here, we're going to call that n. Calculate their partials. So the partial of m with respect to y, x. And over here, the partial of n with respect to x. Okay, that's going to be 4x. Okay, take the difference. Divide by function n. And n is going to be this crazy thing. Okay, then we're going to come through here and integrate. Okay, we're going to be integrating in terms of x. Okay, I'm integrating in terms of x, so how am I going to treat y? Constant. It seems really bad, doesn't it? This problem. What if I was going to give you this problem? You can say, hey, what's the integration of ax bx squared plus c? Here's the b, here's the a in the integral. So just do a quick use of on it. So du is going to correspond to 2b, or not? Okay, take it, drop it in, maybe take the a, push it out. So we're going to get this part, we're going to drop that in, integrate the natural log, absolute value of u, and then the ever elusive plus c, not the same c, the elusive plus c. Drop in the argument. What we did was we made ourselves a formula we can use. Come over here and plug everything in. Okay, you get this. You can always double check to make sure it is valid. What if you take the derivative? Argument goes in the denominator, and then take the derivative what you got up top to get back up here. After you do this, exponentiate. There's your mu. That's what you want to use. Working this problem now, that's hard. Yeah, goodness, this is hard. If you were to integrate this function and you do this in terms of x, good luck. In these situations where it starts getting a little more challenging, there is another way of how we could have recalibrated this factor right here. The other approach is you're going to take those partials and make a slight little discrepancy, slight little difference. The other one you could use is this. And the way you'd actually calculate this is the same way of how we calculated this one. So this is problematic. Let's see if this one actually is going to give us better results. Okay, so back to the drawing board. It is a board. We are drawing on it. Partial, partial. Now, instead of dividing by n, we divide by m. And this one is xy. Okay, which factor do you want to use? This one, naturally, right? That one was way too complicated. Let's integrate it. Natural log of y to the third power. Exponentiate y to the third power. All right, so our integrating magical factor that we're going to use is actually this one. Now let's multiply. Okay. Take this function, integrate in terms of x. And then we have our g function. Then take this function, take its partial with respect to y, and this is going to equal our n function. And again, this is given. And if we take the partial, got something going on here. There's 2x squared y to the third gy. What did I miss? Okay, I made the same mistake I told you not to do. Use this one for n, not that. Use this. 2x squared y to the third plus 3y to the fifth minus 20y to the third. So there again, if you're not getting the right answer, you can use that to self-check yourself to make sure you get the right answer, because the g function should not have a single x in it. It's a good way to self-check yourself. Look at this. Look at that. They need to be the same. They need to negate, and they do. They go away. Now you have the g function's partial, which is 3 y to the fifth minus 20 y to the third. Integrate it. Integrate the left, integrate the right in terms of y. All right, it was a long road, but we got there. All over 2 minus 5 y to the fourth, and the plus c we'll throw that to the other side. And there it is. Wow. That was involved. It's like a one-question exam just for that one question. That's terrible, right? You don't get that one question right, you fail. All right, let me stop, see if you have a question on this. You probably have lots of questions. It probably hasn't really solidified quite yet. But the kind of takeaway is the integrating, it's not really an integrating factor, but it's like the integrating factor where you turn a non-exact differential equation into an exact differential equation. You can hit it with this. But as we saw, this was really complicated at times. So what you would do instead is you'd use this one. And likewise, if this is really complicated, then come back and use this one. Try to make it as easy as you possibly can. And notice that they're really close. The difference is really what's happening down here for the most part. The n, the m. This integrates in terms of x. This is going to integrate in terms of y. Okay. Do you guys feel like you got your money's worth for today? Yeah, I think so. And probably a little bit more on top of it. Okay, well, next time we're going to look at some more differential equations, and we're actually going to circle back around to these types of questions, and I'm going to show you a different way of how to solve these. Yeah, you can solve them by looking at exact differential equations, but there is a nice internal structure within here that we're going to exploit. I'll show you that next time. Okay, you guys have a great day. I'll see you then.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.